So we're gonna have 4 speakers. We'll try to limit the first 3 speakers to 15 minutes, and then the last one can ramble on. In between the speakers, if you have any announcements, like we're doing this, somebody's hiring, somebody, feel free to go ahead and do it. Also, if you want to host a future meetup, or you want to talk, or you want to do a lightning talk, please let me know. We're always looking for people to do that. So, yeah. So, and welcome. Thank you very much for coming. I'm gonna set the timer, so you guys will be like boring. So, my name is Mick. I'm going to talk about reverse caching proxy. So, how many of you guys know what a reverse proxy is? Caching proxy. Okay. Do you guys use it? How many people use it in production, using your production systems? How many people use NGINX for it? Okay. Cool. So I will go quickly about what a reverse proxy is, how NGINX handles reverse proxy requests. I'm going to describe the sample project that I'm using here. I'll describe the problem, the solution, and then the meat of the talk will be I'll just go through the NGINX config file to show you how I do what I want to do. So a reverse caching proxy, basically, it's something that sits between the client and the server. It does a number of things. It handles the TLS termination. It handles compression. It does protocol translation, so from HTTP 2 to 1.1 to 1. It can do load balancing and health checks, rate limiting, so per IP or per second. Access control, so telling you which service binds to which one of your NICs, ports, authentication, authorization, and it also does caching. So when you have NGINX running as a reverse proxy and you hit it, basically what happens is the client connects to NGINX. NGINX reads the entire request. Sends the request upstream, which is the whatever backend server it's configured to proxy for, reads the entire response from the upstream and sends it back to client. And the entire part, those are defaults. This can be changed, but it is actually a very nice feature, and I'll get back later to why it is so. But basically what it means is that your backend server isn't sitting there waiting for the slow client to upload the entire request or to read the entire response. It's NGINX, which is relatively inexpensive, doing the waiting, and once all the data is there, it then communicates in bursts with the server. So that's a nice feature. So the overview of my project, this is my hobby project that I always use to show the various techniques. It's basically a service that shows who owned what patents when. It's an API that's supposed to be machine readable, but also has a GUI on top of it. So it will tell you, like, tell me all the patents that Apple owned in the first quarter of 2014, or show me who owns all the patents pertaining to mobile technology right now. Things like this. So I'm trying to run it on the cheap, but keep pretty rigorous SLAs. The stack is very simple. It's running in the Google Cloud, NGINX, Elasticsearch, and Go. So the basic architecture is client requests hit the REST API. The REST API queries the Elasticsearch, and then massages the results and returns them to client. So what's the problem, right, that I'm trying to solve? I want things to be fast, and I want things to be cheap. Right, and even though this project does it at a very small scale, the same approach is sort of regardless of the scale, you want things fast and cheap, and these techniques will apply everywhere. And I want predictable. I want the system to be predictable. So as the load increases on the system, I want the responses to be consistent. And the context of this is the analytic queries that I'm running against it. So, again, give me the counts of all the patents that company X has in given field. The they're expensive. How many people use Elastic for not for logging, but for not logging things, for something that's not logging? Okay, cool. So you know that, I mean, the same kind of loads apply to log analysis, but analytics when dealing with hundreds of thousands of records can be expensive, right? So what do I do to solve this problem? The need to be fast, cheap, and consistent. Two main things: I rate limit the requests that go to Elastic, and that's to maintain the consistent performance and avoid duplicate effort. And what I mean by that is, given a certain hardware configuration that I'm running my Elasticsearch on, I can benchmark having a representative set of queries that get run against it. I can benchmark it. I can figure out how many concurrent queries it can handle before it starts falling over, what kind of queries it can handle. And so then I can basically use NGINX to limit the amount of requests that get thrown against Elasticsearch up to that threshold, but no more. Once I reach that threshold, I start throwing 503s or 504s. And my thinking behind it is, and I've always advocated it, it's better to have clearly communicated timely errors saying we're out of resources, too many requests, you're flooding me. It's better to have this communicated clearly and early on than to have these things where things get really slow and requests are hanging, but you don't know if you cancel a request and you send another one, what's happening then. I always feel that it's much better to just get very quick and consistent feedback. You either get the response or you get an error, but no like this weirdness in between. So I rate limit the requests and then I cache the responses. So the data set that I have is pretty well suited to caching. It's not updated every minute, every second. The access patterns are also well suited to it. Usually there will be the same query or type of query will be repeated more than once. And what I do, and I'll get to that when I talk about config, but this is sort of the essence of the rate limiting magic that I do with NGINX, that NGINX lets you do, is I abort on timeouts and continue on aborts. So what that means is, let's start with the continue on aborts. When you have a client making a request to your server, the client can, a long-running request. The client can abort at any given point, right? And what can happen then? Well, you could not communicate it to the backend server, at which point the request will continue running, and the backend will not realize that the client went away until it's time to send response, at which point it's basically wasted effort. You could also, the moment that the client terminates, you could propagate this to the backend and say, oh, this is aborted, terminate this. But then again, you lose whatever work has been done up to that point on that request. And when the request happens again, you have to redo it. So what I mean by continue on aborts is, if the client aborts, Elasticsearch will continue running this query and then store the results, cache the results with NGINX. So when the same request comes up again, that work that has been done will be fetched from cache, right? And abort on timeouts is sort of the flip side of this. If, for whatever reason, the request to Elasticsearch just blew up, it takes long, and is just killing the server, then this request should be abort regardless of the client status, right? I hope that makes sense. So how exactly did I go about doing that? These are the key directives. If you read the info on NGINX proxying, a lot of them will be there. I'll go through these. This is just showing the stuff that I'll do. I'll go into them now when I'll go into the actual config file. This is the chunk of the NGINX config file that deals with this. So the first thing I do I just say that the upstream, so the backend service called ES, is running on the same server on the port 9200, right? And then I start going with this. This says that any requests going to the root route on the port 8081, so this is where I'm running my, my reverse proxy, should be just passed to the upstream server that I configured, which is my Elasticsearch instance. This says use the cache that I defined in line 4 that just says where to store the data, how much data. Cache 200 and 302 responses for up to 12 hours. This is the first important line, really. This defines the proxy cache key. So each request that is to be cached needs to have a unique signature so that on the repeat of that request, we can check in the cache, do we already have this? NGINX allows you to, or allows me, to configure that key, to assemble that key from a whole range of variables. Here, it's a combination of the request URI, but also of the request body. Now, the queries that I sent to Elasticsearch, the bodies of the search requests, I construct them in my API. So for a given set of parameters, if I say, give me all the patents for Apple for year 2014, I can always build the query to be exactly the same, right? So I can construct a unique cache key using the body and the request URI, and the URI is just the search route. This is the first rate limiting thing. What this says is if there are more than one concurrent requests for this particular resource, only do one at a time and have the other ones wait until you get the response. So if I have 3 requests doing the same query against Elasticsearch, only one of them will actually hit Elasticsearch. When the response comes back, that will be put in the cache, and all 3 requests will return the value from the cache, right? So that's in essence, you know, what the reverse caching proxy does for you. You remember how I was talking earlier about not duplicating the effort. This is what I mean by not duplicating the effort. And this is the other half of it, ignoring the client aborts. So if the client decides halfway through an expensive request, I don't want it, continue doing this request, get the results, and put them in cache. Because oftentimes, well, you know, one of the most common use patterns that I see is somebody hits a long-running request and then aborts halfway into it and then reloads immediately, right? That in itself, you know, and it's kind of one of these things that the worse things get, the worse that gets, right? This is the way, so the combination of this and the one above, this is how you safeguard against that. That's you know, that's, I like that, that's awesome. This is the stuff that I was talking about, aborting on timeouts. It basically says that if we don't get the response within 5 seconds, abort it, something's wrong. And what that means is that this, in combination with the cache lock and also the rate limiting per IP, means that if the server starts getting overwhelmed by a huge number of requests, it will just sort of gracefully, at some point, it will stop accepting new requests. It will return errors on the ones that have timed out. And what it really means is that because I had before benchmarked my system and I know how many requests it can deal with, I will never get to a situation where it just stops responding. Where, you know, I'll always have, I have the guarantee of basically a 5-second SLA. You will get a response, either a correct response or an error, but you always will get it. And that's regardless of, you know, how many concurrent requests you're running or whatever. The response will always come within 5 seconds. This one here, if there are errors, allows you to use an old value in the cache. And the last 2 ones are sort of more diagnostic. This allows me to bypass the cache on per request basis. I use this mostly for debugging. And this adds a header to the response reporting to me, was it cache miss, cache hit, whatever. So I can incorporate this into my logs to measure the performance of my cache. So just wrapping up some thoughts. So caching is really cheap, right? You need disk, but other than that, there's really no penalty. There's no reason not to do it. Even if, like a lot of times it's like, oh, my data changes all the time. Well, what's the resolution? What's the actual resolution at which your data lives? Like, is 1 second acceptable? Is 5 seconds acceptable? Is 30 seconds acceptable? Like, even 5 seconds, just TTL of 5 seconds in your cache can be a big deal. If you have somebody just clicking the same thing, refresh, you're saving a lot of hits to your backend, right? HTTP is awesome. The NGINX plus Elastic, that's a great thing. You get so many things for free using HTTP. You get encryption, you get caching, you get load balancing, all of these things that you get different protocols. My backend talks only HTTP 1, but I can have clients talk HTTP 2, 1.1, whatever, because NGINX does the termination for me and then just talks to the backend in 1.0. So that's nice. And so that lets me keep the API simple and have all these other things be dealt with by NGINX. Couple of tools for debugging. And well, actually, I'll skip this, but my actual setup is a little more complicated. I have another caching proxy sitting in front of my API because with analytic requests to Elasticsearch, if I'm doing a sig terms aggregation, it doesn't actually matter performance-wise if I get 10 results or 10,000 results back. It's going to be about the same as far as the expense goes. So every time I query Elasticsearch, I'll query for 10,000 results, and then my API will par it down to whatever the client actually requested. And that's it. The thing is on GitHub, what I just showed. And yeah, thank you very much for listening. And I'll be around if you want to ask. Okay, we can do a couple of questions. Yeah.
Well, pretty much you save results for 12 hours. You assume you not get through to much of new data.
Yeah, so I mean, with this data set that I work in, the patent office publishes the data daily, so that's not a biggie. But even if you're dealing with log data, as I said, if you can decide that your results have to be only within the last 5 seconds or 10 seconds or 30 seconds, you can save yourself a lot of processing power just by caching even on this small window, right?
Yeah, I've got another question about cache size. If you mentioned you run this in Google Cloud, you have to pay pretty much also for space and for speed units, yes?
Sure.
So, like, what's kind of, did you make some calculation, like what is more convenient?
Yeah, it's money, right? Like, I could just have a monster cluster of Elasticsearch machines and run all of this without cache. Disk is so much cheaper than CPU and memory that it's just much more efficient for me to run it with cache and store the results in disk. Yeah, please.
2 questions. One is how do you make them do what you're doing? And the other is, like
it's just willpower, man. It's just like,
the other question is, do you have a lot of problems with cache pollution? Where is your audience for your site the public?
Right. So this is an excellent question, and I don't let anybody run random queries against my Elasticsearch, right? Everything is filtered through the API. So I hit the API, I pass what I want to search for, but the query is constructed by the API. So I do a lot of cleanup before I build the queries, right? And I also, as I said, I make sure that the queries are always constructed in the same way. So for example, if you did naive query construction, if you were searching for Apple Inc. and for Inc. Apple, those would be 2 different queries. I can sort the terms and make sure that it is essentially the same query. So, yeah.
Thank you.
Good.
Is there a cache starts to fill up? Is there like an eviction policy?
I don't have, well, so there's the time, and also I didn't, in the top line, where you see line 4, it ends with saying max size 1 gig. It's gonna do least recently used eviction. So, sorry, the next people have to go.
Yeah,
so.
we gotta move it on, sorry.
Thank you, everybody. And if anybody has any announcements, now go ahead.
All right, thanks, Shannon. So I'm going to be doing a demo with NGINX and Docker. So I'm curious, I'm guessing, have most people here familiar with Docker in the room? Okay. And I always saw a lot of hands went up with NGINX. So I'm not going to spend a lot of time talking about that, but I'll show you, actually see it in action. The idea here was to do dynamic scaling. So automation is fun. I'm guessing most people here like to write code to automate things. In this case, I wanted to be not only show how you can sort of automate something in a manual fashion, but how you could actually dynamically automate it, so you could be hands-off and watch your system adjust. So that's kind of what I did here. So I'm using NGINX and Docker. This is something where, again, Docker is a great tool for spinning up and down services and containers. So for those of you who haven't used it, and you'll see how simple that is. Oh, okay. This is better? All right. And then NGINX Plus, which is the commercial version of NGINX, has a few features that I'm going to use here. One is the dynamic configuration API. We have a couple of ways of allowing you to scale your backends up and down without having to reconfigure NGINX. And I'll be using one of those here. And then I'm also using our status API to monitor traffic, and I'll show you the dashboard. And then I've also written a program in Python that actually does the scaling. It's going to actually look at that status API to see what's going on and then react to it. So this is it's a pretty simple configuration. I've got NGINX Plus sitting there as a load balancer. On the back end, I've got NGINX as a web server, and I have Elasticsearch. And I'll show you how I'm scaling both of those. And then the auto-scaling program is one that I've written that sits externally using the APIs to both monitor NGINX and cause it to scale. And just a warning, so this is strictly demo. This is not production quality code. So hopefully to give people ideas, but don't try to run this in production. It's all run on my laptop. So all in one Docker host, so not at all a production level system. Let's get on with the demo. Sorry. There we go. So I've got a bunch of scripts here, and I'll just show you a real simple one now. So this script here actually creates my environment. It runs 3 other scripts. So I'm going to create a container in the load balancer, a container for Elasticsearch, and a container for the web server. Hard to see here with this mic here. So I'm using just raw Docker commands here. So there's a lot of tools in the ecosystem now to spin up Docker containers and so forth, but I'm just doing really simple stuff here. So you see here, I'm just running a Docker container. I give it a name, my NGINX Plus, and I'm using an image that I created called NGINX Plus Load Balancer. So if those of you who use Docker and go to Docker Hub, you'll know that NGINX is one of the most popular images downloaded from Docker Hub. But Docker Hub is not gated, so you can't put commercial products there that unless you have some sort of license keys, which we don't. So if you want to use NGINX Plus in Docker, you have to create your own image with a simple Docker file. And I can show you, if I have time, I can show you it here. But it's on our website. I've written a blog post that shows you how to do that. It's not hard to do at all. And the other scripts, I'm going to, just for the sake of time, I'll skip over that. I'm sorry. The scripts for creating the Elasticsearch and the NGINX nodes are also very similar. Just fire up a container. But in that case, you'll see here, if you're in the Docker Hub, it's called port mapping. Because you have multiple containers on the same host, they can't all share the same ports. For here, for my load balancer, I'm actually saying I want to use the real ports. So in this case, 80 for the load balancer, 8080 is from one of my APIs, and then 443 for SSL, and then 9200 for the Elasticsearch. For my other containers, I'm allowing Docker to do the port mapping, and I just grab that later on. Okay. So if we run that container, that script, hold on here. Hope it's better because I can't see what I'm doing here. Let's first show that we have nothing running. So if we do a Docker PS, that shows we have no containers running. If we run that command, we'll see that it just fired a bunch of containers. If we do our Docker PS again, we see 3 containers. So there's our Elasticsearch container, There's our web server container, and there is our load balancing container. And if we go look at what we call our dashboard here, again, it was empty originally because it wasn't running. I'll see my NGINX system here. And this is my system-wide information. Again, we're talking a very simple system here. Again, the upstreams, for those of you who don't know NGINX, those are the back-end servers that are being load balanced. And we have my NGINX backends, those are my web servers, and my Elasticsearch. Again, I had one of each, which you guys saw when I did that script. But it was easy to spin up one. It's just as easy to spin up multiple. So I can go in here, for example, and we'll just add, we'll add 3 Elasticsearches, for example. We'll see that took less than a second each, and now I have 4 Elasticsearches. And if I want to kill them, I can just remove some of them. And now we're down to 2. So Docker is really cool, and that's why my team, we do all our demos in Docker, because we can spin things up and down so easily. Also very low resource. If you're used to doing demos in virtual machines, my laptop here, I can get 4 or 5 virtual machines, and then it starts really slowing down. I can spin up 20, 30, even 40 containers and hardly even notice it. Again, the containers aren't doing a lot of work, obviously, in this case, but I can do that really well. So let's run some traffic here. I've got, I'm using Siege, if you're familiar with Siege, a load generation tool. I've got 2 scripts, one for generating load traffic to my web server and one for the Elasticsearch. It just runs an infinite loop, and every iteration, it randomly decides how long to run and how many connections to open. So you'll see the traffic going up and down. If we type it right here. So that's going to generate some load to my web server. And this will generate some Elasticsearch load. So now we'll see we've got requests running on all of these guys. So that was sort of showing how you can deploy stuff, and obviously you can script this and run it, and it runs really fast. What I thought was the more interesting part was how could I dynamically scale this? How could I have a program without me having to do anything, watch this, and actually scale up and down? So I've created a Python program that is using this API. This dashboard is sitting in front of a REST API giving JSON data back. So I just make periodic calls to it, and I figure out what's the request per second per server. And I've told it for the NGINX backends, I want to keep between 10 and 12 requests per second, maximum of 10 nodes, minimum of 2, and it can scale up 4 at a time and down 2 at a time. For Elasticsearch, I've told it to keep between 5 and 7.5 requests per second, and scale up up and down 1 at a time, and again, minimum of 2, maximum of 10. Now, a node in Elasticsearch, when you add a node to a cluster, there's some time it takes to come up live there. So for those, when I scale the backends for Elasticsearch, I have after I create it, I actually wait a while before I add to NGINX. Otherwise, it's going to come up and fail its health checks, because I have health checks going here. So it takes a few seconds to get in here. That's not true of NGINX, because it's not having to join any clusters. So those scale immediately. So let's go ahead and run the auto-scaling programs. So this one is going to auto-scale NGINX backends, and this one is going to auto-scale the Elasticsearch. And we'll see there, I think there was one here before, and you'll see how fast that's scaling up and down. And the Elasticsearch one is going to be a little slower because it scales and then it waits for a few seconds, but it will eventually fire up here once they come alive again. There you see it's added a 3rd one there. So these can go up and down. You'll see my request rate just dropped a lot here, so it's going to start scaling back. So the idea here, again, is just to give you an idea. Again, there are multiple ways of doing this with NGINX and NGINX Plus. But again, Docker is such a great tool for being able to easily spin up a server and just blow it away whenever you need to get rid of it. And you see how fast it can react here. So this is, I mean, that's NGINX. Or I have a program querying the API, it's telling Docker to spin it up and edit here, and it all takes almost no time at all. If we were to kill our load, well, as I told them to go down to a minimum of 2, so these are both going to eventually drop down to two nodes. There you go. Go down to time. Okay. Yeah. So we have some time here, I think. We have some more time? I can show some more of the scripts. Perfect. So let me just kill this. So just to show you what the, well, it's probably up in here. Let's actually give more space for showing things. There we go. If we look at the auto-scaling program, again, I wrote it in Python. You could choose any program you wanted, obviously, or language you wanted. It's not terribly complicated. I've told it what's the API for my status API. That's the API that it's checking to see what's the current load. And then what's the API, what's the URL for the API to scale? That's what it's doing here. What's the name of the upstream group that I'm scaling to? And here's where I have my minimum, maximum, how many you can add at a time, how many you can move at a time. So this could all be parameterized. Obviously, I just, for my demo here, have it all hard-coded in here. Again, what's the request rate I'm trying to hit? So basically, it's that. And after that, it's just going through a loop. It has to get the node count, so it knows how. Basically, it's taking the total number of requests divided by the node count is the request per second. And it actually is looking for healthy nodes, so it's actually taking into account if a node is down, it doesn't count it. And then it just loops. Again, it just loops forever, and each time it checks, it basically says, what's the current? What's the target? Am I above the target? Then scale up. If I'm below the target, scale down. And it just actually it's calling the same shell scripts that I ran earlier. Again, you could use the API, but actually reading, a lot of people weren't very happy with the Python Docker API. So I stuck with my shell script. So it just calls a shell script and says, please add that. The same exact scripts I ran by hand. And if we want to see, let's go back here. Again, for Docker, as I said, you have to create your own Docker file, but it's not a difficult thing to do. What I've done is created a base NGINX Plus image. And if you're my blog post, this comes directly from my blog post. Any of you who have actually used NGINX Plus, you will have gone through this installation process. It's not complicated. We don't have any license keys, so we protect our repo. You get a certain key, and that's what it's copying here, in here, and a couple other files. So it's basically just downloading some files and then doing it. And in this case, I'm doing an apt-get install of NGINX. I can. Just a second here. So you see, I'm exposing ports 80 and 443. So pretty standard there. But you may have seen when I started up my my load balancer, I also exposed 9200 and 8080. So for that, I created a different Docker file. It just takes my other one and exposes 8080 and 9200. And I have another one for load balancer where I actually wanted to copy my content, so I'm mounting different volumes. So again, if you haven't used Docker, you should actually take a look at it, because you can just build these images, and then you can build other images off that image as a template. So we ask about config files. That means I have to remember where I put it. Oh, there it is, I see. So this is my Docker configuration. So you'll see I have upstream groups here. Those of you who are familiar with NGINX open source will be well aware of that. You may not know about the zone command. The zone command is what allows us in NGINX Plus to do the dynamic configuration. But you notice I have no upstreams in here. It's empty. So I'm actually starting with an empty upstream. And then they only get added by using the API. And other than that, you'll see it's pretty simple. I've got health checks running. I've got a back-end program that just says OK or error to give it to do that. And so I'm matching that. And you see a simple listen directive. If you saw his, it's very similar to that, because I'm not doing any caching. I do some sub-filtering here. If I do a more full demo, I can actually show the actual pages coming up, and it'll say what server, and you can watch it load balance and so forth. And then for Elasticsearch, again, nothing terribly fancy. You will see I have some of the same timeouts that you saw in the previous one, the 1 second. Again, my demo here, it's all local. It should be running really fast. If it's taking longer than a second, then I have a problem, and I want NGINX not to continue to wait. And then I've also got my status API here. So I've got it on port 8080, just listening on that, and you'll see this is, again, an NGINX Plus feature to get that dashboard that you saw. That's about, again, I'm happy to go and show anything else if you have any questions, but those are sort of the main features of that. Again, there's a whole bunch of other scripts. This will get up in GitHub. We're actually we're trying to get that set up so we can put our demos in GitHub, so that will be in hopefully not too distant future, this stuff will be up there. So hopefully I'm okay on time. Yeah. Okay. Yeah, any questions? Yeah, yeah. Yeah, so what you saw here, the two things that are NGINX Plus are the zone directive and the upstreams. What that causes NGINX to actually, all the workers are going to share the config and the dynamic configuration. That allows me to do the dynamic configuration. And then what you actually see, actually I don't see it here, another part. So that's the one feature, and then the status API. So basically those two APIs are what I'm using. Again, I'm using the status so I can see what's going on, and then using the upstream API to reconfigure it. You can also do dynamic DNS. That's another way of doing it. We have a lot of customers who actually add and remove the upstreams from DNS and then have NGINX re-resolve that periodically. They can grab it that way as well.
Feature was the health check to check for the page to return the OK,
Right.
and not the something else in the page.
Right.
So the open source version of NGINX will take the server out of the upstream if it's completely unavailable, if it fails the connect or read timeout. But this one will take it out of the load balancing group if it returns something other than OK, even if the server is returning a 200 response code. So the
So
intelligent
literally
health
the
check.
string OK.
Yes.
Yes,
That's
that's
what,
yeah.
status OK.
Yeah, that's what this health check is basically hitting. I have a file called healthcheck.html. In a real production instance, those are commonly written in PHP or something else, and they actually may do a database lookup and so forth, and then return OK. Mine is a text file for demo, and I actually have a version that says error and a version that says OK. You know, when I have more time for the demo, I actually cause them to fail to do that. And, like, you see them go red and so forth. But yeah, so that's another one here. I didn't use that in my demo. This demo has that in there, but I didn't have time to go through that.
Thank you.
Welcome. Any other questions? Yes.
So as you're scaling up Elastic, Elastic will start to store data on the different nodes,
Yeah.
or shards. When you scale them down, what is the data that's stored there?
I'm not an Elasticsearch expert. Maybe one of our Elasticsearch experts can answer that question.
Depending on the replication, right? But if you go from 100 to 2, where's the
It
data?
depends on your number of replicas. So if
Yeah, but replica 1, right? Or
It's
replica 2.
partition that between-
That's not gonna. Yeah, that's not a standard configuration. That's not a standard configuration. It wouldn't be. I don't think you can scale up irresponsibly of scaling down without proper replication.
Well, so I think your question, like, you definitely want to make sure that you don't spread your shards too thin, right? So given how many primaries and how many replicas you have, there will be an upper bound of how many nodes you want, and there also will be a lower bound of to how fast you can scale down, right?
Yeah.
As you're taking nodes out, you have to rebalance things. So yeah, and unless you have 200 replicas for each shard, then scaling down from 200 to 2 will lose your data. Like that's
That's what I'm saying.
essentially
I
turning
didn't
cluster,
see
right?
any
So you'd have to
responsibility
add
for
those
verifying
checks.
that the replicas there were enough
Yeah.
replicas.
So you remember, yeah, my warning about not being production? This is just showing ideas, exactly. But that's why, but it does have upper and lower bounds and how many you want to scale at a time. So, and you could add lots more stuff in there. Yeah, my initial demo just scaled the NGINX, but since we're Elasticsearch meetup, I go, I should scale the Elasticsearch too. But yeah, so if you were doing a real auto-scaling one, there's a lot of stuff you might need to take into account. Again, for the NGINX, you don't. You're free to do that, but Elasticsearch isn't, you are just more involved, which is why I had to have even the timer to say you can't just immediately throw it in. You have to wait for it to be ready to go. Okay, thank you.
As Shannon said, my name is Ilya. I'm from a company called ViveWorks, and we build tools for Docker. I mean, previous talk was involving Docker. I guess quite a few of you have heard of Docker and containers in general, right? Is this better? Yeah, I was just asking how many people know Docker. And do you know it well? Did you build something on it? Did you just played with it on one machine or something like that? You have anything running on Docker? All right, cool. Well, a few people did. All right. Well, all right. I mean, well, what Docker did, it defined a unit of deployment for your applications. And it's great, right? We all agree. It's like, whoever tried it, it's pretty awesome, isn't it? It's all like build, ship, run, anywhere, seriously, this time. Okay, well, yeah, however, there are a few things to it. And when you come to run Docker containers on different machines and you want to connect them together, that's not exactly straightforward. You have to figure out port mappings, host IP addresses, what's going to run in a host namespace, what's going to run in its own namespace. Are you going to breach those two? And all these jazz. It's kind of getting quite complicated. So a year ago, even a bit more than that actually. We've released the first version of EveNet, which is an overlay network for containers. It allows you very easily connect a bunch of Docker hosts together and run containers with unique APs for each container. And then you can use default ports for all of them, forget port new mapping. Also multicast works in different clouds. It's an Elasticsearch meetup, so actually you might care about how you do Elasticsearch discovery, and the multicast discovery on Weave works right out of the box. And we also have DNS, and hey, NGINX Plus has DNS support, right? You can dynamically configure your upstreams based on what's in DNS. Or how are you going to do that? Are you going to go and stand up some DNS infrastructure and write config files like that for every little thing you've got? Or grab some guy's Perl script that generates that? And, well, you know, I mean, you might as well get that book, and it's like, O'Reilly will sell it for $4.99, and it's 642 pages. You get a better deal on Amazon, but whatever, you know. You might try to read that. You probably give up pretty soon. And go with like some DNS as a service and then figure that out. But why should you pay anybody for anything for your internal stuff? With Beef DNS, you can actually write a simple NGINX config file just like that, right? So you specify your resolver somewhere there. I mean, didn't care too much about that. That's shown in the demo how to do that exactly. And then you pointed at your app.weave.local, just to resolve it. You might specify some extra options anyway. And then you just do that, and then, you know, basically how you get this this whole my app Weave local thing in the first place. Well, you just run a container like this, right? That gets this DNS entry automatically. And you can run as many of these as you like on any host. And you don't have to care about the ports they're using. You just run as many as you want. Whatever kind of host you have, you might have some smaller ones, some bigger ones, I don't know. Whatever, just start a bunch of these in a loop. You'll be fine. The NGINX will see all those DNS records and pick them up and use those as backends, right? And then, well, okay, that's cool, right? Kind of easy. Then if you wanted to run Elasticsearch in container, there are multiple angles at it. Okay, storage is one thing. That's something we don't do, and you might want to look at Flocker or some other things like Flocker. I don't think there are many storage solutions. There's only Flocker by ClustHQ. There are a few alternatives to networking stuff that we do. However, I'll explain the advantages of how we do stuff later on. So Elasticsearch, right? There's an official image. You just docker run minus d Elasticsearch, boom, you got an instance. Well, you probably want to run a cluster. And then, all right, well, we're going to start a cluster on one host. This guy, ITGZ, I don't know him. He, or her, I don't even know. Anyway, I found that on GitHub. You can do those. Great. That's not an official image. What can I do with an official image? I have no idea. Figure it out. Okay, well, yeah, I mean, you'll spend a while figuring this out. And how are you going to map these ports? Or are you going to use like host networking and then care about what IP addresses they leave on? And who knows? Yeah, as I said, yeah. What are those ports supposed to be? Maybe I should register them. Maybe I then learn about like this ambassador pattern and what's that? All right, I mean, I could put an NGINX in front of each of these things or some other load balancer. Jesus, right? Gets quite complicated pretty soon. Or maybe I'll use one of these fancy orchestration tools. Maybe I use Mesos with the Elasticsearch framework. That only came out recently. So there are various things, but you're still new to containers and all these things. You just want to get up and running. And you don't want to research all these different options. This is a bit old. Maybe there are a few more, but that's something I found like a few months ago. Yeah, great. Okay. So there's a quite specific ones. Look almost solid, usable. Got some stars on GitHub. Cool. All right. Well, yeah, anyway, just forget all of that and seriously with Vive, you can get an Elasticsearch cluster running pretty quickly. And it comes with DNS. It's really simple on the client side, and you can use it with any of those orchestrators as well. Okay, but you can start without the orchestrator bit. You'll figure that out later. You don't need one right now. I don't think, unless you've looked into all of them and you seriously think you have to use Mesos. But then yeah, you can come at that angle too. Okay, and yeah, as I said, it's super simple. Like that's like a JavaScript example. I connect to a cluster of 3 nodes, and that's what I do. Okay, and that's quite straightforward, isn't it? I didn't have to use any of the. I don't know why it doesn't have a default port. I had to set column 9200, but anyway, if the client knew about a default port, like I wouldn't have to specify that either. And actually, Vive.local is also optional. Just a bit of branding right there. Okay, well, I've done this demo where I'm using Elasticsearch with a little RESTful and Node.js API in front of it, which sort of like tries to manage some documents in Elasticsearch and make certain things a bit simpler. And I can just use curl to post things into it. It's really like a silly little app. I didn't have a specific purpose, just to illustrate how a RESTful API could sit in front of Elasticsearch, and how we could put NGINX in front of that. Okay, so I've got 3 VMs, which are Docker hosts. I've got Vive set up, which is super simple. I mean, if you take a look at our docs, it's like you just run 3 commands, and you got network up and running. And I've got an Elasticsearch instance on those, on each of those, and 2 instances of my RESTful app on each of those VMs, and NGINX load balancer, load balancing across all 6 app instances on each of the machines. So I can hit any IP address, almost like in Kubernetes, but without using Kubernetes. And yeah, it works, right? I'll show you that. I mean, and then actually all of these things can run on completely different hosts. So I could have 3 separate VMs just for Elasticsearch, some VMs just for NGINX containers, and some VMs for my app instances, and it will work exactly the same way. I don't have to care anymore where these things are running exactly. Okay, so yeah, let's jump to the demo. Boom. Okay. Right, what we've got? We got 5 minutes or something, Shannon? Right. Okay, cool. All right. Well, I'm on one of these machines. Sorry. Okay. So I run Vive state. As I can see, there's there's one failed connection. That's great. All right. Oh, that's fun. Okay. Oh, yeah, exactly. We've got Vive running here. And, right, well, yeah, it's a demo, right? Let's see. All right, cool. Yeah. All right. I've just reconnected my Vive peers. It's like because I've traveled from the office to here, and sometimes the external network connection goes down, and who knows what's happening. It's VirtualBox as well. It's flaky at times. Anyway. Right. Okay. So now we're back to we have 2 connections. So there are 3 VMs, and each of those has two connections to the other peers. Right, so Vive status command is kind of useful for that. And then you can run Vive status DNS to see what's in your DNS. And what we got like 6 instances of my app, all right? And an Elasticsearch. Oh, actually, I've upgraded to 2.1, and something changed in the discovery. Maybe I need to change some flags. So anyway, I promise I'll fix it tomorrow. When you get to run it, so on the slide there was a link to this to these instructions here. What happened? All right. You know, when you get down to run this, I'm sure I'll fix the Elasticsearch clustering part. Okay, so we got these apps, and if I check, oh, is this connection? Oh, Jesus! All right, we're back. Okay. Fun. Okay, well now it's cables. Huh. Yeah, we're pretty good now. Don't have to dance, hopefully. All right. So you can see there are 6 instances of this my app thing. So if I grab for my app, I've got 2 instances here. And this is Core 02, and if I grab for my app here, there are another 2 instances here, and there's Core 03. Trust me, there are another 2 instances there, right? And if I do Viv DNS lookup my app, I will get 6 IP addresses here, right? And we can kind of see by the prefix that they're on different hosts. But those are dynamic anyway. Okay, cool. I also have NGINX running here, you can see, which sits in front of all of these apps, but on each of the hosts. So I can hit any of these. Okay. Right. Already print that. Right. I can hit. This is Core 02. I can hit Core 01, and this is just the slash on Elasticsearch. But then I have a little API here that I've made up that I can talk to, so I can post some messages to it. All right. This is the latest version of this thing. I think there's a later one, so let's just quickly look at this API thing. All right. Yeah. So there are a few endpoints here. Okay. So we can get and root. That gives you the Elasticsearch status, I believe, name and stuff, and then we can post a title to hello index. We can get that title and we can search for it. Okay. So where are we? Oh, there's one I haven't documented. I promise I'll update the docs. So I can post to this guy. All right. So now I can post this first one, and I'm posting some data, where it's like can everybody see this well? Cool. All right. So I'm just posting a little map into this thing, a JSON document, and call it, and the title is sample 1. Okay. Just that. All right, we got that. And we walk through this, and if you can see, I'm hitting different IP address each time here, right? So that was 102, 101 here. So I can pick any random one of those. I'm still getting through this. And okay, there's a second thing, whatever that did. Oh, it posts a duplicate document under the same title, okay? So now, by the definition of this API, if I call this, all right, there are too many of those things you have to search. It's Elasticsearch, right? So we're gonna search. Boom. Okay, we got sample 1, A2, sample 1, A1, right? Okay, that's it. I mean, we can see it's functional. I'm sorry, the cluster broke right last minute. I haven't tested the clustering part in 2.1. I really kind of fancied upgrading. I could have used the older container that I've had, but you know, I promise I'll figure that out tomorrow, as I said. Okay, what just happened, really? Okay, as I said, I've got 3 machines. I've set up Docker on those. Actually, it's CoreOS. Docker is installed, cool. And then I set up the network with Viv. which is something you'll find in our other docs, and it's super straightforward. Really, you just type leave launch, and then an IP address of at least one other host. Okay, and that gives you everything DNS and everything. And then what you need to do val venv, and from there you talk to the leaf proxy. You can learn more in the docs. But the purpose of this demo was really a kind of an application demo, rather than not how you set the thing up. And we've used all the pieces, NGINX and Elasticsearch for it. And if we showed a little simple way of running a DNS server without having to configure one, right? Like it's super simple that. Okay. And we are in this demo directory here. There are some Docker files for my app, okay, and the actual implementation JavaScript code. My app LB is the child image of NGINX Plus image. I've built the image slightly differently, and that may be of interest to some people. And I'm relying on the latest Docker 1.9 feature called build argument, where I can specify some random strings that I can then use to download the certs that, at build time. Anyway, that's fun. And then there's the little script called bootstrap sh. That is just simple Docker commands. Again, not using Compose or any orchestration tools. Okay. Well, I think maybe we could jump into a few questions if there's time. Cool. All right, fine. All right, one question, the most boring question. All right. Next. Thanks everyone.
So, thank you all for staying late. I promise I won't be offended if you have to leave. I know we're running late here. But if you do stick around, I ask that you hold your questions until the very end, and I'll be happy to stick around and answer any questions later. So, can you hear me okay in the back? Okay, thanks. So Elasticsearch 2.0 came out about a month ago, and there are a lot of changes. I'm hoping to cover a fair number of them today. There's a lot to cover, so I'm going to go pretty fast. I apologize in advance. Oh. That's really close. It's okay. Maybe I'll just hold it. Actually, yeah, that might work. Okay. So yeah, my name's Shaunak Kashyap. I'm just gonna hold it. My name's Shaunak Kashyap. I'm a developer advocate at Elastic. Little bit about Elastic. We're the commercial entity behind Elasticsearch and other open source projects like Logstash, Kibana, etc. We do like to pay our developers, so we have some commercial plugins for Elasticsearch that are at the bottom there, and we also have a hosted Elasticsearch as a service product called Found. Just to be very clear, Found has nothing to do with the AWS Elasticsearch as a service, completely different, no partnership, nothing. That's all I'm going to say about that and move on to Elasticsearch 2.0. So, as I said, it came out a month ago, and it was a pretty large release, more than 2,500 pull requests from about 460 plus contributors. Our company is only about 300 people, so obviously a lot of those contributions came from the community. And one little project I'll mention, I'm very proud of is we did this little thank you card giveaway where we sent stickers to every contributor with handwritten note for contributing to 2.0. And that makes me really happy because it makes me feel like, you know, our company Elastic, even though it's commercial, we do care about the community and we're being good open source citizens. But that's not what we're here to talk about. We're here to talk about what's new in Elasticsearch 2.0. So the main focus with 2.0 is just getting more mature, just growing up, and a lot of times that means, you know, simplifying things, making things more robust. We actually added very few features, and that's because when it comes to adding features, we just add them in our minor releases, our minor version releases, and those come out once every 6 weeks or so. So in 2.0 proper, just a couple of features were added. Most of my presentation will actually talk about what was removed and what was moved out of core into plugins, etc. And then finally, there's some impact on plugins as well, good impact in 2.0. So as I said, we're simplifying things, and that means removing a lot of things. Now, just to be clear here, everything that I'm going to talk about that was removed in 2.0 was deprecated in some 1.0 version, so none of this should be a surprise, hopefully. So what's not in 2.0? Oh, sorry, I just noticed this. Here we go. What's not in 2.0? Rivers are gone. Rivers were deprecated a while ago. What we ask for now is use Logstash or write your own script or program to do the ingestion from third-party sources. Facets also gone, replaced by aggregations. The shutdown API is gone. There is no corresponding, or there never was a corresponding startup API, so it doesn't really make sense to have a shutdown API. Plus, it was kind of a bit of a risk. You know, you have a cluster, you can shut down the entire cluster, but just by calling an API. So we took it away. And there are way better ways to control the life cycle of processes. So just use those system or platform specific methods rather than relying on this weird API. We found that people actually weren't using thrift and memcached protocols as much, so we just simplified and took them away. Same thing with bulk UDP. So if you want to bulk ingest or index documents into Elasticsearch now, either just use the standard bulk API, which is HTTP, so over TCP, or use the Logstash UDP input if you really want to send data over UDP to Elasticsearch. So that's everything that was totally removed. It's gone from 2.0, doesn't exist anymore. But what's here is things that used to be in the core, Elasticsearch core, but now have been moved to a plugin. So you can still use these things if you want, but you would just have to install a plugin. Delete by query wasn't quite atomic and was causing out of memory errors, so it's now a plugin. And by the way, the plugin has been implemented using the scan and scroll API, so it's a little more atomic. These two types, murmur3 and size, they're again fairly obscure, not a lot of usage, so we moved them just in an effort to keep core really, really small and minimal. You can still use them if you really want to, they're in a plugin. Multicast, the reason your demo broke, sorry, was multicast discovery. Yes, multicast discovery is now a plugin. By default, if you just install Elasticsearch, you have to use Unicast. I'll talk a little bit more about that later, but that would be why. A lot of the simplifications were around mapping changes. There are a lot of mapping changes. I won't cover all of them, but I'll cover some of the important ones. So in 1.x, if you specified a mapping like this, Elasticsearch would happily accept it. The problem with this is you have two fields that are both called name, and they're both part of different types, and they have slightly different definitions, right? So in 1.0, this would be okay, but this is a problem. This doesn't quite work as you might expect at query time. So what we've done is in 2.0, we just don't allow this. So if you really want two fields with the same name in two different types, they have to have different mappings, or you can give the fields different names if you want them to have the same mapping. Or sorry, I got that backwards. If you want two fields with the same name and two types, they have to have the same mapping, 2.0 onwards. So here's a question. In 1.x, let's say you have this mapping and you are running a query. And in your query, you are referring to title. What do you think title refers to, given this mapping? Like, there's titles in two places, number 2 and number 4. What do you think title would refer to if you used it in a query? Would it refer to 2 or would it refer to 4? Which field would it refer to? It could actually be either. It would match both of them. So in 1.x, both would work. Another question, what about name.title? So here name's a field and title's a subfield. Here name's the type and then title's the top level field in that. What would name.title refer to in 1.x? Yeah, same thing. Of course, name.name.title is not ambiguous. It's name.name.title, and in 1.x, it would refer to just that field. But obviously, there's a lot of ambiguity here, so we decided to get rid of that and make things unambiguous. So starting with 2.0, title, the namespacing starts at the top level of the fields. So when you say just title, it'll refer to the top level title field. When you say name.title, it's going to refer to the top level name field and the title subfield within it. And something like this, name.name.title, is now just invalid. Basically, in other words, you cannot prefix the type name when you're referring to a field. You can't use that as a prefix. So this is just to make things unambiguous. Obviously, these are all breaking changes, so need to be aware of those. Field analyzers. So when you specify a mapping, you can specify how you want a field to be analyzed. And that when you set an analyzer like that, you're telling Elasticsearch, okay, use that analyzer for indexing, but also for searching. So before 2.0, there were 3 settings that you could use to set 2 analyzers up. You could use the analyzer to set both the index and the search time analyzers, and then you could override each of those or both of those using these specific settings. That's one setting too many. You don't really need all those. You can just do it with a simpler way, which is set the analyzer and then optionally override the search analyzer, starting with 2.0. So this makes it easier if you're looking at a mapping. It makes it hopefully easier to figure out, just looking at a mapping, exactly what analyzer is going to be used when. There are many other changes, and we don't have time for them. So I'll put a link to this presentation in the meetup, and then you can follow the link over here. There's a great blog post going over all the little changes as well with mappings. Query and filters, the execution has changed for the better. Before, you had to, if you wanted to use a filter, you had to wrap it in this little filtered query in the DSL. Not anymore. You can just use a bool query, and this is a query, and so there's a must and must not clauses, etc. But then there's an additional clause called filter, which lets you add a filter to a query. So the DSL is a little different in 2.0. And when it comes to executing the query, things are a little better. Things are a little faster now. So if you look at this example, earlier, before 2.0, Elasticsearch would run this match phrase and then do an intersection of the documents to figure out what the final set is. Now it's a little smarter. So it does it in 2 phases. It'll do an approximation phase where it'll first gather all the documents that have all these 4 terms in them. So the documents have to have all 4 terms. And then it'll discard any that don't match these 2 specific phrase queries. So there's an approximation phase and a verification phase. So another example, a more visual example of this would be, imagine you had a geo-radius search. So Elasticsearch in the approximation phase would first create a bounding box that contained that circle. And quickly, that's a much faster geoquery to get all the points in a bounding box. And then in the verification phase, it would discard anything that's not in the circle. Does that make sense? Okay. Filter caching, so filters were always cacheable, except with 2.0 now, we have made the caching automatic, the management of the cache automatic. So the key things to remember are what Elasticsearch will do is it'll keep track of the 256 most recently used filters. If a filter appears 5 or more times in that list, it'll cache it. And there are some exceptions. It'll just because sometimes it's faster to run the filter than to go to the cache. So it tries to account for those with these 10,000 documents or 3% exceptions. And then another thing I'll mention is the data structure that we use to cache filters has changed. So earlier, filters, the data structure was just a bitmap. So each bit position signified whether a document matched the filter or not. And if the bit was 1, that means the document matched the filter. If it was 0, it didn't. What we've done is we've made it even more efficient than that. We were using roaring bitmaps. Roaring bitmaps are, you can think of them as, imagine a bit set and divide it up into a bunch of blocks of a certain size. And then for each block, what roaring bitmap, the way it works is it determines if that block is sparse or dense. If it's dense, so a lot of 1s in there, it'll use it as a bitmap, so nothing will change. But if it's sparse, so there's a lot more 0s, It'll instead just store the lists of the document IDs, like an array of document IDs. So, and it does this combined data structure is called a roaring bitmap. So this way, what gets stored is actually very, very, very efficient. We made some additions to security. We've tightened things up, really. Elasticsearch now only binds to local interfaces. Earlier, it would just bind to all interfaces, so you can hit it from anywhere you want. As I said earlier, unicast is the default, and the reason for this is, in production, we always recommend that you run unicast anyway. We never recommend running multicast in production. And because we don't want a stray node somewhere joining and maybe issuing a delete and everything's gone. So most of our customers or users in production will run unicast, so we've made it the default. Of course, as I mentioned earlier, if you really want multicast, you can install a plugin. And then the other thing I'll mention with unicast is if you were to download Elasticsearch today and run, say, up to 5 nodes on the same machine, it will auto-discover. So there is this weird sort of, it's still unicast, but while it's on the same local interface, it'll auto-discover the first 5 ports in your port range. So the reason we sort of settled on that compromise, by the way, there was like a 70 email long thread internally about discussing this change because it was like a classic usability versus security thing. The reason we settled on this compromise was because we still wanted to enable the starter use case of like install and go. But we also wanted to make the default be closer to what people do in production. And now Elasticsearch runs everything via, or accesses all the system resources via the Java Security Manager. So, if Elasticsearch itself is compromised, there's a bunch of policies that have to be followed. So it's not as easy to get to any resources that Elasticsearch is accessing because of the Java Security Manager. This is a big one. So before 2.0, the transaction log would be fsynced to disk either when it filled up or it hit the every 5 seconds. Now we did some tests, some performance tests, and we found that it's actually not that bad to fsync the transaction log on every operation. So now that is the default. Of course, you can tune it, but that by default now, every index operation will get fsynced to disk each time. So, and there's some numbers telling you like how much of an impact that has. It's not that bad. So this makes Elasticsearch durable now by default. That did not used to be the case. There's a way to, on a single node, to tell Elasticsearch where to store the data. And so this is best explained via example. So let's say you had 4 shards, and each shard had these files. Before 2.0, this is how these files would get distributed amongst multiple data paths. So basically, a single shard's files could end up on different data paths. And that wasn't great because if you lost a data path, a volume, you could affect multiple shards at this point. So starting with 2.0, what we've done is a single shard's files will all reside on a single data path. So even if you lost this data path, only that shard is affected, at least, or only the shards on that data path are affected, not multiple shards. So it's a little bit better that way. This is another big one is before 2.0, the entire cluster state would be sent over the network whenever there were a cluster level change, which means as your cluster grew, number of nodes, their cluster state itself grew, and so that would become a limiting factor for how big your cluster could be. Now we only ship deltas, so you can grow your cluster quite large. The other nice thing with this change is that it lays the foundation for something like cross data center replication down the line. Now that we have deltas, it's a lot less chatty over the network, so it would be possible to ship these across the network and do cross data center replication, which is another feature we're working on. This is a good one. So pre 2.0, let's say you issued this API call. Can anyone guess what has actually happened here? Like, we're obviously changing the refresh interval for that index, the test index, but what if we change the interval to? Yeah, so 5 milliseconds is the right answer, but Most people guess 5 seconds. Thanks, Mick. But anyway, you don't know, basically, right? You don't know. So what we've done is, starting with 2.0, we've required units. So you can't accidentally kill your cluster because you just didn't know what you were doing, and you're not Mick. So right in 1.0, we had doc values and we had field data. Doc values has improved a lot since 1.0. So now it's become the default. So when you create a new index, any field that is not analyzed will get doc values, and doc values are kind of like field data. So it's like a uninverted inverted index, but they're stored on disk as opposed to field data, which stays in memory. Which means because of doc values, you free up a lot more memory for other things. Now, of course, this only works going forward. So if you upgrade to 2.0, doesn't mean all your old indices automatically get doc values. Any indices you create from this point forward will get them. For time series data, that's not a huge deal because the newer indices with newer time series data will get doc values, and that's where they really come in handy, is for aggregation and sorting, etc. But for older indices, you would have to reindex. This is the smallest section in the presentation, which is what new features were added in 2.0. This is a really nice feature of pipeline aggregations. So aggregations are like sums and averages, etc., or buckets that you can apply to your individual documents. Pipeline aggregations are aggregations on top of aggregations. So you take the results of aggregations and then you do aggregations on top of them. So basically, if you have, you're looking at sales data and you have, June had so much sales and July had so much sales, but you can run a pipeline aggregation to say, okay, what was the delta between June and July, and then July and August, and so on. So that would be the derivative. Or there's moving averages. So that's a moving average with a window of 10. So it gives you a nice little sort of smooth curve that fits your data. If you want an even smoother curve, you can up your moving average to a window to 100. If your data is seasonal, you want to use the Holt-Winters model. So the moving average aggregation has a property called model in the API request, and you can specify Holt-Winters, and it works very well for seasonal data. So pipeline aggregations were a big feature in 2.0. Also, index compression got better. So by default, Lucene used LZ4 for its index compression. But starting with, I think, Lucene 5, might have been 4, but starting with 5 for sure, deflate was introduced. So deflate is the same thing that I think gzip uses. Deflate was introduced, and the reason that was done was because LZ4 works really good for text data, so the classic full text search use case, but doesn't work so well for analytics, the analytics use case, where your fields, the value of your fields tend to be really, really small. So by using deflate, we found that the compression is much better. And so you can do that now. You can there's a setting at the index level that you can say, set the codec to best compression, and it will start using deflate instead of LZ4. You can also set this at a node level, so every index that ends up on that node, every shard of the index will get that compression. And you can use that along with the hot-cold sort of setup to ship your, if you have time-based data, you can keep the most recent data on a hot node and have that use LZ4 and have your older data as it ages move to colder nodes and have that use deflate. And the reason you want to do it that way is because there is a cost to using deflate. There's a little bit of a penalty you pay during merging when segments get merged. So you want to defer that cost until you're ready to move the data to a cold node. Plugins. Now plugins are, a lot of the core plugins are now built as part of Elasticsearch. So before 2.0, Elasticsearch would come out, and then a few days later, the core plugins would come out. Now they just come out at the same time, and they also get built and tested with Elasticsearch during the build. So which means we won't release a version of Elasticsearch if all the core plugins don't pass and work with that version of Elasticsearch. Also, because plugins, the core plugins are bundled with the Elasticsearch release, you no longer have to worry about versioning. So you don't have to look up this version matrix to figure out which version of the plugin will work with which version of Elasticsearch. Now you just install Elasticsearch and then you just specify the core plugin name and it will install the one that is compatible with the current version of Elasticsearch. So if you are thinking of migration, and you should, 2.0 is a major release, so you want to be careful. You know, it's a one-way street, and make sure you have a backup. You can't do a rolling upgrade. So these are just some things to remember. We have created this migration plugin that hopefully will help. So you take your 1.x cluster, install this plugin there, and run it. It'll generate this report of all the things that need to change for successfully migrating to 2.x. And basically, you just want to keep fixing these until this report becomes blank. And then you can migrate to 2.0. And that's it. These are all our usual means for getting help. We have a discussion forum where obviously we're on GitHub and IRC, and there's always Stack Overflow. Oh yeah, and then we're having our user conference in February. This is our second one. I think early bird pricing ends in a couple of days. So if you're interested, go to that link and buy a ticket. That's it from me. Thank you very much.